Hello and welcome back to Aerospace and Mechanical Lab 2. Today we are going to talk about the heat transfer lab. We essentially review the theory and talk about the lab itself. You want to keep in mind that this lab needs a full lab report, not a worksheet. You want to write a full lab report, which is what we always do for the second lab of the lab series. Okay. Again, today we're going to review heat transfer, the science of heat transfer itself. We will specifically focus on transient and steady heat conduction and forced and free convection. And then we will move on to talking about the lab itself and how to do the lab. Okay. First thing you need to know is what is heat transfer. To understand heat transfer, though, we need to understand what temperature is. Temperature is essentially just the amount of thermal energy available in a system. Because the temperature of the system depends on the energy source, essentially how much heating or cooling you are going to see there. And the type of energy source can be, like for heating, can be solar, natural gas, and so on and so forth. Heat transfer or heat flow is essentially movement of this thermal energy from one place to another place through different mechanisms, right? The amount of heat flow depends on the mechanism of heat transfer first, and then the medium at which this heat is being transferred. So there are two things we need to learn about, or different types of different mechanisms of heat transfer specifically. So for different mechanisms, the first one, the most common one, is called conduction. Conduction is the transfer of heat through solids or stationary fluids by direct physical contact. The idea is pretty simple. If you look at anything from a molecular point of view, you have molecules that are connected to each other through bonds, right? If you heat up one of the molecules, they are going to start vibrating, and this vibration is going to be transferred to the other molecule through these molecular bonds, right? And these are going to be at higher energy states, meaning that they are going to be hotter, and then this heat is going to be transferred to the other molecules and so on and so forth. And that's how the heat is transferred in a solid or a stationary liquid, by each molecule transferring its energy to the next and to the next and to the next. From a macro perspective, we are essentially going to see a valve like this, in which the temperature on one side is larger than the temperature on the other side. If they have this sort of scenarios, there will be heat transfer from the hotter side to the colder side, right? So that this energy is going to be transferred, this energy of these molecules is going to transfer to the next layer of molecules, and so on and so forth. Another mechanism for heat transfer is called convection, which essentially uses the motion of fluids to transfer heat through advection and diffusion, right? This is different from conduction in that the higher energy molecules are themselves moving to replace the lower energy molecules. So the energy is not transferred from one molecule to another. Simply a higher energy molecule is going to replace a lower energy molecule through different mechanisms. Advection happens where a bulk of higher energy molecule essentially move to a lower energy area. Diffusion happens when the higher energy molecules, start diffusing at all directions, right? Two different mechanisms for convection. Of course, for this type of energy transfer to happen, you need to have molecules present that can move freely. That doesn't happen in solid, that only happens in liquids and gases, fluids in general. So convection heat transfer is only limited to fluids. We have two different types of convection heat transfer. One is natural convection, which is essentially the fluid movement is created by heating. Think of a water boiling in a pot. You start heating the pot, and the hotter molecules that are closer to the heat source are going to move up, and that is going to cause some sort of a movement, some sort of a fluid flow inside of your pot, right? That is called natural convection, essentially the movement of fluid that is caused by the density change, the energy change between different molecules. Another type of convection is called forced convection. Forced convection simply uses an external source to move the fluid, right? When you don't have an external source to move the fluid, you are dealing with natural or free convection. When you do have an external source to move the fluid, you are going to see forced convection. Example of forced convection are in cooling devices that we see whenever you are machining something. Like in a boiler jet, when you want to cool on your solid with the movement of water, that water is being pushed onto your whatever you are machining, onto your sample using a pump or whatever. That is an external source of movement for water, but you also see heat transfer. This is called a forced convection scenario. Okay. Another type of heat transfer is radiation. Essentially, it is the only form of heat transfer that can be present in a vacuum, meaning that we don't need molecules anymore. We only need electromagnetic waves or photons, depending on how you look at the essentially light transfer, energy transfer. So this type of heat transfer, again, is done through electromagnetic radiation, then can move at the speed of light. The radiation heat transfer is not going to be a part of this test. I just wanted to make sure you understand what different types of heat transfer are present. Radiation is one of them. Let's go back to the solids. To quantify the amount of heat flow in a solid, we need to use the Fourier's law of heat conduction, which is the mathematical theory of heat conduction that was developed by Fourier. I'm sure you have heard the name Fourier. He is the reason behind a lot of advancements in mechanical and aerospace engineering and in all other types of engineering and science. So the theory says the heat rate, essentially the amount of energy that is being transferred through this solid medium right here, is related to the conductivity of that solid, essentially the resistance that solid has to that heat transfer or the lack of that resistance, right? Multiplied by the cross-sectional area, which is this cross-section that is normal to the direction of the heat that is being transferred. So this cross-sectional area multiplied by the temperature difference divided by the thickness of the wall. This is a very simplified way of looking at the Fourier's law of heat conduction. This equation assumes that there are no heat sources in the wall itself. So the heat sources are outside and are pushing heat throughout this wall, right? And it assumes that there is no transient changes. Everything has reached a steady state. What that means is that these temperatures do not change with time. And you're going to see later on how that becomes important when we are running our test, our heat transfer test. Okay. And the idea in the lab would be for you to measure all of these temperatures. You are going to know the heat rate, and your goal would be to calculate the conductivity of your specific sample that you're using in the lab. The transient conduction or convection part of the lab is pretty simple. The idea is we are going to see how much exposure to an outside air is going to help you cool down a heated copper block, right? And pretty simple. When you have heated copper block, you put it in air, you are going to see convection with the outside air. We are going to give you a fan. You're going to put that fan in front of a heated block and then another heated block without the fan, essentially simulating free and forced convection scenarios. And we are going to ask you to calculate how strong is going to be the convection heat removal. Okay. the assumptions we are making here is that the conduction inside that copper block is happening instantly. So the changes of temperature of the block only depends on the time that has passed, the transient part of it, and the convection with the outside air. That is the assumption we are making, and we are going to test whether this assumption is correct or not after we have done the experiment. Again, essentially the temperature is the same across the solid wall and only changes with time, meaning that the conduction is instant. Conduction happens at a moment. This method of analysis is called the lumped capacitance method. For those of you who have taken a transfer course, I'm sure you have seen this method a lot. The idea is pretty simple. We are going to neglect conduction in favor of convection. And if you do that, the energy equation simplifies to this specific equation that is going to give us the temperature at any time t as a function of surrounding temperature. Essentially, this is your outside air temperature divided by the initial temperature at time 0. This is essentially the temperature of the copper block whenever you started doing the experiment, and it is equal to the exponential, or e to the power of negative h. H is the strength of air, essentially, in removing heat. How strong air is in removing a heat transfer coefficient. This is equivalent to the conductivity of solids, but only for fluids. You want to keep in mind that this is not a value you can easily read off of a table, because it does depend on the velocity of air and temperature of air that is moving. So you definitely need to calculate these values for your specific scenarios. So this heat transfer coefficient multiplied by the area of the copper block, this is a cube, so 6 times the area of each side of the block needs to be included, divided by the multiplied by time that has passed, divided by the heat capacity of copper, multiplied by volume of the copper. So the idea is, in the lab, you're going to use the DAQ that we have to come up with this type of graph. You start with a temperature. In this graph, we have dimension as temperature and dimension as time. You do not need to convert your calculations to dimension as time and temperature, but the graph you're going to see is going to look like this for both free convection and forced convection scenarios. And then you just essentially take 2 of these points, put it in this equation to find heat transfer coefficient. And the idea is you can take as many 2 points as you want on this graph, meaning that you can have more than one heat transfer coefficient calculations, meaning that you can and must do a statistical analysis. Okay. Well, in the beginning of this, we said there is a limit to the validity of the assumption we made about the convection scenario. Where is that limit? And that limit shows up in the Biot number calculation. So the validity of our assumption that we made, and the assumption was the conduction is negligible. We don't need to include conduction in analysis, which helped us to come to this equation. Right? So the idea is the Biot number, the dimensionless number that compares the internal resistance, conduction, to external resistance, convection, in this specific scenario, has to be much smaller than 0.1. So essentially, we can calculate the conduction resistance by 1 over conductivity, and we can calculate the convection resistance by 1 over H, heat transfer coefficient, multiplied by L, which, if you play with that equation, you simplify the equation, the Biot number can be calculated as heat transfer coefficient multiplied by the length of the beam divided by the conductivity of the solid. This has to be smaller than 0.1. So essentially, the idea is you calculate the heat transfer coefficient, you find an average value for it using the statistical analysis, and then use that average value here to investigate whether the lumped capacitance assumption was correct or not. Okay, so the lab itself is going to look like this. This is the linear conduction apparatus that we have in the system. You see this white part is essentially an insulation that we have to make sure that the heat transfer is one-dimensional, so we can use a simplified version of the Fourier's law. And then we have installed thermocouples that look like this at 8 points of the system on the metal that is inside itself. You are going to cool this bottom part of your sample, heat this top part of your sample using this heat supply, and then you have to wait for 20-25 minutes for everything to become steady, and that's when you can do your calculations and record your data. Again, the idea is pretty simple. The amount of heat rate is equal to conductivity multiplied by the area divided by delta x, which is the thickness, multiplied by delta t. This is a type of graph you will get out of this test, essentially temperature with respect to time. And after, again, 20, 25, 30 minutes, the temperature of each of these thermocouples stops changing with respect to time. That is when the steady state conditions have been reached. And that is when these are the data, these are the temperatures you can use to put this in delta T. Essentially, you have 8 measurements, meaning that you can easily have 7 delta T's, and you can easily do your calculations for the conductivity of the beam. Second part of the test is pretty simple. You will be given a copper block that is connected to a thermocouple. That thermocouple is connected to a DAQ. You heat it up, then you simulate force and free convection. You let it cool down in front of your fan or freely, track the temperature, and then eventually measure the heat transfer coefficient. Again, a statistical analysis must be done for this lab as well as other labs. And you want to make sure you understand that you need to write a full lab report for this lab. Thank you for watching the video. Please let me know if you have a question or concern.